perhaps book it is not given, but you can try my things. Like for example, one thing, I'm not a control man, right? But one thing, small thing. For example, you have studied initial value theorem, final value theorem in control system. Studied or not for finding out the steady state error? Got it or studied or not?
Yes.
Initial value theorem, yes, studied. No. Now you take any block diagram. I didn't try this one. Book you will not find. Just listen carefully. Suppose when it's an integrator, suppose ki upon s is transfer function, right? If s tends to 0, then you put s is equal to 0. Integrator case, I have not tried. But any steady state error, you take any block diagram, right? So when t tends to infinity, s tends to 0. Right. That means that t tends to infinity is steady state. That means in the block diagram itself, you put s is equal to 0. Then whatever block diagram will get, that is steady state block diagram. Based on that, you find out steady state error, all will come automatically. You need not derive the transfer function, another thing, then go initial value, final value theorem, other thing, right? Or sometimes initial value theorem, nothing is required. If you put it, you will find the steady state error for all the state variables, right? I thought automatic generation control, that part, whatever is there, book you will not find, but whatever I am telling, you can match. It has to match, right? Because I know this, right. So anyway, so I'm sharing this and the stability part, right? Power system stability part, and this will be last one. Automatic generation control I will not add, but I will suggest when you return to the campus next week, yeah, at least not all, some of you can meet me in the department, but after 11 o'clock, right? So just I'm sharing my screen now. Is it visible? Is it visible to all of you?
Yes, sir.
Okay. Now power system stability, right? So first, I think little bit you have studied your what you call in control system stability. Meaning of stability, different topic, different specialization is different, but ultimate goal will remain same, right? So in general, when you define stability, the stability means that ability of any system to return to its initial condition following a disturbance. Suppose if some system is disturbed, right, and after some time, if it comes back to its initial condition or in the vicinity of that, then the system will remain stable. That is the concept of the stability, right? And power system is the your largest man-made dynamic system on the earth, right? So that's what the different type of stability is there in electrical engineering. One is steady state stability, that is a steady state power carrying limit, other thing. Another term in the, here it is written in this book, that is dynamic stability. But nowadays that word, that sentence, dynamic stability, has been changed. It is now small signal stability they call. Any latest book you will find small signal stability. Now, and another is transient stability. So but whatever we study, little bit initially, little bit of steady state stability and transient stability for single machine infinite bus system, not multi machine. And small signal stability will not study. That is dynamic stability, because the small signal stability topic is huge PG level, right? In a semester, that small signal stability, actually we have a one PG course called Power System Dynamics Control and Monitoring, right? So dynamics and control. So there the dynamics part, the small signal stability part, it takes 60% or more for a semester, because many things it has to be covered, right? So small signal stability will not consider here. Even that thing also for multi-machine system we cannot teach in the class, because it is a huge thing, your that modeling of synchronous generator. And another thing is transient stability. Transient stability, here we'll study the basic thing for single machine infinite bus system, right? So generally what happens when loss of synchronism will mean to render system unstable, right? So this kind of all these things happen, right? That when system is your what you call becomes unstable. So in our country, that so your in a power plant, a thermal power plant, say that your alternator, that our synchronous generator, you will find it is basically two poles, and it revolves, and frequency is 50 hertz. So ns is 120 f by p, so it is your 3000 rpm. If it is 60 hertz, it will be 3600 rpm, right? But all the time you will find in the power system disturbance is there, because sometimes some load will be switched off, sometimes load will be switched on. This process is continuous. The disturbance will be there, but it is not like that system will go fall out of state or system will become unstable, right? So continuous disturbance will be always there in a power system. But anyway, that is small signal stability, but we will not study in this course, right? So steady state stability relates to response of the synchronous machine to gradually increasing load. You are increasing the load, but up to certain limit. After that, your system may lose synchronism. As you have not done your what you call that laboratory in our department, right? Because of pandemic things. Otherwise, this power angle characteristic of synchronous generator, right? A synchronous machine, you should have seen in that your machine lab. Long experiment, and for that all these things little bit you should have learned from that, right? But as whatever you have done it, that is through online. But had it been in the lab, then you should have in power system lab particularly, then you should have learned that one, right? It is basically concerned with the determination of the upper limit of the machine loadings before losing synchronism, provided that loading is increased gradually. Right. So dynamic stability, that is small signal stability, involves the response to small disturbance that occur in the system, producing oscillation. This we will not study. It is a very lengthy topic, right? I told you in PG level also it takes 60% time of a semester. And system is to be dynamically stable if these oscillations do not occur more than certain amplitude and die out quickly. In reality, nothing die out quickly. Continuous oscillation or continuous disturbance will be there in the system, right? So, and if this oscillation continuously grow and never dying out, means system is going you're unstable, right? So, and transient stability involves the response of generally it is written the system response to the disturbance may not become apparent for some 10 to 30 seconds. And transient stability involves the response of a large disturbance, that is a fault, right? Previous chapter we have seen line 3 phase fault, line to line fault, line to ground fault, right? So this kind of thing involves transient stability, and here only we'll see the basic thing: single machine infinite bus system for transient stability, but not for multi-machine system, right? And if you consider multi-machine system, classroom exercise you cannot do. You need a I mean through software and computer simulation, then only one can analyze. It is not possible to do it your what you call by as a classroom exercise. Now inertia constant and the swing equation, right? So in electrical, your what you call that whenever you have studied your what you call that is your first year single phase AC circuit, when you started, generally I used to explain to the student that that how the theta electrical, this you have studied from machine I believe, that theta E electrical is equal to P by 2 theta mechanical, right? So this is your electrical, and if suppose it's a 4-pole machine, mechanically it will rotate your what you call 360-degree, right? But if it is a 4-pole machine, so it will be 2 times your 360, right? So that electrical and mechanical is a different one. So I used to cover this in the first year before your what you call that your before going to studying your AC single phase AC circuit. So anyway, that will come. That's why I'm telling that inertia constant and angular momentum play an important role in determining the transient stability of a synchronous machine, right? Physics you have studied that inertia constant, moments of inertia, everything. So power unit inertia constant in H is megajoule per MVA, right? When we write that your unit inertia constant H, we write in electrical engineering, that is your, suppose if it is megajoule, before moving that, if it is megajoule per MVA, right? So joule per second is equal to watt. That means it is megawatt second, then MVA, right? So power unit system we have studied megawatt upon mega MVA or megavar upon MVA is dimensionless. So this is second, right? Therefore, our electrical engineering, this your inertia H actually is in second, right? This way later it will come that power unit inertia constant H is megajoule upon megajoule per MVA. It is nothing but in second. So that way we represent in our electrical engineering as the kinetic energy stored in the rotating parts of the machine at a synchronous speed per unit MVA rating of the machine. So rotor kinetic energy at synchronous speed. Rotor means it is generator turbine actually together, all these together because it is coupled together, right? So kinetic energy will be half into in a motor your inertia J into omega s. This is mechanical speed, right? Same relationship. This is your same relationship. If it is theta e up is equal to p by 2 theta m, then when you write your synchronous and electrical one, then this side will be synchronous speed and this side will be electrical one, right? WE or WSE we have represented, right? So this is actually K is equal to half J omega s square mechanical into 10 to the power minus 6 mega joule, right? So we have divided by 10 to the power 6, then it is megajoule. So here J is moment of inertia of rotor, that is kg meter square, and omega s mechanical is equal to synchronous speed in mechanical radian per second. Therefore omega s electrical is equal to p by 2 omega s mechanical. The same thing, right? This is the same thing that your here I wrote the electrical angle is equal to mechanical angle into p by 2. The same thing here, that your omega s electrical is equal to p by 2 omega s mechanical, that is number of poles. P is number of poles, right? And therefore if you substitute omega s electrical is equal to p by 2 omega s mechanical here, if you substitute, then you will get K is equal to half J into this thing you write in bracket. It is omega s electrical square and it is omega s electrical 10 to the minus 6 into omega s electrical, right? And this bracket portion we define as M. M is equal to J 2 by P square into omega s electrical into 10 to the power minus 6. This we also define moment of inertia in megajoule second your per electrical radian. This way we define. That is your M. That means kinetic energy will be half M into omega s electrical. This way we define. Now we shall define the inertia constant H such that G into H, right? G is the 3-phase MVA rating of the machine and H is the inertia constant megajoule per MVA or megawatt second per MVA. So megawatt per MVA is dimensionless. Basically it is a second, right? Therefore we define that inertia constant is such that G into H is equal to kinetic energy is equal to half of whatever you have got it, M omega is electrical, right? This much of megajoule. And units are mentioned. Therefore M is equal to 2gh upon omega is electrical, right? If it is in radian, then 2gh upon 2 pi f and is equal to gh upon pi f mechanical joule, megajoule second per electrical radian. And if you want in degree, then M will be G upon H 180 F. So this will be megajoule second per electrical degree, right? Now M is also called the inertia constant. Assuming now G as a base. Suppose G is the your what you call that your 3-phase MVA rating of the machine, and if G is the base, then both side you can divide by G, right? If you divide both side by G, then your M per unit, right? This M or this M GH upon pi f, if you divide by G, M per unit will be either this one H by pi f second square upon electrical radian, or M per unit will be H upon 180 f second square per electrical degree, right? So this is actually the joule per second is equal to what? So joule is equal to watt second. So megawatt second square, right? And you are defined by G. That's why this second square has come, right? So now this is a standard inertia constant of the machine. This is I have taken from a reference book. Like turbine generator, if it is rotate 1800 RPM or so, say H will be in between 9 to 6 seconds. If it is 60 Hz, then 3600 RPM, it will be 7 to 4. Then different units have different things are there. Like slow speed, like water turbine, it will be 2 to 3, 2 to 4. Some table is there, right? So different inertia constant. Actually what you do from field test, they actually compute all these things, right? So typical inertia constant of a synchronous machine. Now little bit if possible I'll zoom it, otherwise so now if here one thing is there, here one typographical error is there. This output will be electrical power PE. Here it will be your PE, right? This is the typing is missing, that it will be your, I'm putting it here, right? That arrow is going, no, it will be PE, that is electrical power, right? So whenever you choose, this is input power, this is electrical torque, right? All these things, and this is TI, right? Now question is that suppose your consider a synchronous generator developing an electromagnetic torque T. This is your electric. I assume it is a lossless, right? We are not considering the loss. So lossless T and the corresponding electromagnetic power is P. This is P. I told you it is a typographical error. P is not here, right? Missing. It is PE, right? While operating at the synchronous speed omega s, this is omega s. If the input torque provided by the prime mover at the generator shaft is Ti, right? Prime mover here, it is turbine generator coupled together, right? It is no gear mechanism, nothing, directly coupled together. So turbine also rotate at a 3000 RPM for a 50 Hz system in all to the thermal power plant. In hydro power plant, number of poles are more. So, I'll not teach automatic generation control. There things are there, everything is there, right? And your what you call, and the shaft is, that is your torque provided by the prime mover generator shaft is Ti, right? Then under steady state operating condition without any disturbance, T will be is equal to Ti. That means your it is lossless. We are assuming totally lossless, right? Therefore, if you multiply both sides by omega s, then this one you can write Ti omega s minus T omega s is equal to 0. In general, P is equal to T into omega, therefore Ti omega s is equal to Pi and T omega s is equal to P. So Pi minus P is equal to 0. It is perfect when everything is balanced, right? And totally lossless. This is most ideal situation. Now, if there is a departure from steady state occurs, for example, a change in load, suppose load has increased or decreased, or a fault, then input power Pi is not equal to P, right? If the armature resistance is neglected, we will assume that it is neglected. Therefore, left side of the equation, that is this 12, right? That means this side is not 0. So Pi minus P will not be 0, and an accelerating torque comes to play. If Pa is corresponding accelerating, it may be decelerate also, because load may increase, load may decrease, right? So it may be decelerate also. Then we can write this equation that Pi minus P is equal to m into d square theta upon dt square plus d theta e of dt is equal to Pa, the accelerating power, right? So where m has been defined in equation 8 or equation 9, d is the damping coefficient. For this study, we will not consider the damping coefficient, right? But damping also through experimental studies, they find out for large system, but here we will not do, right? And theta is the electrical angular position of the rotor. Whatever we say, theta is equal to P by 2 theta m. It is more convenient to, actually laboratory, if you have done power angle characteristic, then you should have an idea that with the reference signal, how that the change of load, how that angle is shifting, whether it is generating mode or when it is in motoring mode, right? But that is only possible in laboratory 10 or 11 degrees, not more than that, right? And it is more convenient to measure the angular position of the rotor with respect to synchronous rotating frame, because machine is continuously rotating, right? So, in general, time is increasing. So delta, you can write, is equal to theta e minus omega s into t, right? Because it is continuously increasing and it is measure the angular with synchronously rotating frame or reference, right? Actually, in the laboratory, that 0 to 360 degree, everything is marked, and you have to mark it by reference, by chalk, right? And when you are pressing the stroboscope, because and it is fixed, and when you're increasing the load, then you can check the difference of the angle, right? But as you have, I don't know, online you might have seen it, I'm not sure, because in laboratory, when you are doing this, at that time you will see that, right? Therefore, delta E, therefore, if you take your delta E is equal to theta E minus omega s into t, then d square theta upon dt square, theta E upon dt square is equal to d square delta upon dt square, where delta is the power angle of the synchronous machine. That part, your power angle or torque angle characteristic of synchronous machine, that in third year power system lab, the student do. Right. Now, neglect damping, d is equal to 0. And if it is so, then this equation can be written as that d squared theta e upon dt square is equal to d squared delta dt square. Therefore, m d squared delta dt square is equal to pi minus p, right? It is megawatt. Now, if you substitute the value of m, then from the previous equation we have seen, that is gh upon pi f is equal to into d square delta dt square is equal to pi minus p in megawatt, right? Now, both sides, if you divide by g, then all these thing will be per unit. M also will be per unit. Therefore, M into per unit d square delta dt square is equal to Pi minus P. It is also per unit, right? I have written every time megawatt or per unit, such that when somebody will read, that there should not be any confusion, right? So this is both side divided by G. So this is megawatt. So it will be converted to per unit. So M per unit d square delta dt square Pi minus P both per unit, right? And M per unit we have seen before, H by F, right? So now H pi, therefore H by pi f d square delta upon dt square is equal to Pi minus P per unit, right? So this is actually called swing equation, right? I mean, and later through some graphical representation I'll show you, right? It describes the rotor dynamics for a synchronous machine. Although damping is ignored, but it helps to stabilize the, it is not stabilizer, it helps to stabilize the system. R should not be there, right? Damping must be considered in dynamic stability study, that is your small signal stability study. Tangent stability study also you consider, right? But damping will not consider here because things will become complicated. And now this is your what you call your swing equation. This is required again and again. And multi-machine system. Now suppose in a multi-machine system will not study anything, just that per unit system, common base, those things. Multi-machine system, a common base you can choose, that is G machine is equal to machine rating base, and G system is equal to system base. Machine is machine base of machine rating, and G system is the overall system base, right? Now suppose that, therefore what one can do is, suppose this equation is H pi f d square delta dt square is equal to Pi minus P, right? Therefore it is G machine upon G system. Suppose it is H machine, if you make it, for example, if for this equation if you write that H machine by pi f d square delta upon dt square, right, is equal to, it is given Pi minus P, right? So multiply both side by G machine, this equation both side you multiply by G machine, right? And if your system base is G system, then what, divide by G system. First you multiply this equation both side by G machine, then it will be your what you call, instead of H, inertia should be H machine, right? So G machine, H machine, and this is also multiply both side by G machine, right? That is the machine base divided by the total system base, right? So system base will be more than the G machine in general, right? Therefore this equation can be written as, this is H system upon pi f, because G machine, H machine upon G system, so converted to per unit, and this is also converted to per unit or system base, where H system is equal to G machine upon G system into H machine. That is machine inertia constant in system base. As your test will be or your offline and closed book, so please little bit of practice is necessary, right? Now another thing is machine swinging in unison. That means in a power plant, any power plant, if nowadays, no, technology has developed a lot, right? And things are, with the time, things are changing many things, right? And for the future, perhaps at that time I may not see all these things. Before that, you know, the people will come, people will leave this world, but technology will go on developing. When you will grow, maybe after 20-25 years, right? That now things have started on very fast, it is going on. That is called virtual power plant, right? These are coming up slowly and slowly. Everything is totally your software based, and they call IoE, that is Internet of Energy, right? And that is in near future it will be like that only. Maybe power plant will be based on battery energy storage system or some renewable sources, right? And it will be totally your software based. They call virtual power plant. Microgrid, smart grid, nanogrid, islanded microgrid, grid connected microgrid, all these electric vehicles, right? So many things are coming up, but virtual power plant is already based on existing power system. Some places in the world it is there, but new things are also coming up. That it will be no question of coal, fossil or this thing, coal or hydro or water, nothing. It is based on battery energy storage. Of course, at present battery is very expensive. I mean, but with the technology, it has been observed that as technology will develop, everything will go down, and some new thought, new discovery, new invention will come, and this way technology is developing, right? So now machine swinging in unison. Unison means they are decrease or increase speed will remain same. Suppose in a power plant you have 4 synchronous generator, right? We are assuming that they are swinging in unison. That means they are in coherent group. That means their increase or decrease speed will remain same. This is your assumption and fairly good assumption, right? The swinging in unison means they are all these, suppose 4 machines, 5 machines are working in parallel, their increase or decrease speed will remain same. That means they are in coherent group, right? That is the meaning. So suppose swinging equation 2, suppose 2 machine you consider. Suppose one is inertia h1 upon pi f d square delta upon dt square pi1 minus p1. Another machine say h2 upon pi f d square delta 2 is equal to this one, right? And as they are they are swinging in unison, so delta will remain same for both the machine. Therefore delta 1 is equal to delta 2 is equal to delta. Therefore in general we can write h eq pi f d square delta upon dt square is equal to pi minus p, where pi is equal to, because you add equation 24 and 25 and substitute this one. So this 24, 25, 5 you add and then you substitute because they are swinging in unison. Therefore pi is equal to summation of these two, p is equal to summation of these two, and h equivalent, that is this one, is equal to h1 plus h2. Equivalent q can be expressed as, suppose machine 1, it's a G1 machine into H1 machine, that is rating of the machine, divided by the system base, plus G2 machine into H2 machine divided by the system base. System base is common, right? But machine rating is this one multiplied by this one, and G2 machine into H2 machine by G system. G system is common, that is your H equivalent. So these equations are simple, but you need little bit of practice, right? Even enough time is there, you practice. Right, now take this example. A 60 Hz 4-pole turbo generator rated 100 MVA, 13.8 kV has an inertia constant of 10 megajoule per MVA. 10 megajoule per MVA is nothing but 10 seconds, huh? Because in electrical engineering, we represent H in second. In exam, you may not find megajoule per MVA, it may be in given second, right? So now you have to find out the store energy in the rotor at synchronous speed. If the input to the generator is suddenly increased or raised to 60 megawatt, for an electrical load of 50 megawatt, find the rotor acceleration, right? So if the rotor acceleration calculated in part B is maintained for 12 cycles, right? Find the change in torque angle and rotor speed in RPM at the end of this period, right? This is the problem. So first you have to find out this data are given, 60 Hz 4-pole, 100 MVA, 13.8 kV, and H is given 10 seconds, right? Therefore, find the store energy in the rotor at synchronous speed. G is 100 MVA is given, H is equal to 10 seconds is given. Store energy will be G into H, so 100 into 10, so 1000 megajoule. So first part is simple. Now second is, if the input to the generator is suddenly raised to 60 megawatt, for an electrical load 50 megawatt, for find rotor acceleration, right? Input has increased, that is Pi minus Pe. So suppose it was balanced, now it has suddenly increased. So that Pi is more than your electrical one. So machine will start accelerate, right? Therefore, Pa is equal to accelerating power Pi minus P, that is 10 megawatt, right? And M, we know GH upon 180F. So GH we have computed 1000, 100 into 10, and 180 into 60 Hz system, 100 into 180 into 60. So it will be 5 by 54 megajoule second per electrical degree, right? Now we know m d square delta upon dt square is equal to accelerating power. This equation you have seen. Therefore 5 by 54 d square delta upon dt square is equal to 10. Therefore d square delta upon dt square will be 108 electrical degree per second square, right? Because here we have your what you call, we have taken in degree. If you take it in radian also, then you can make pi f, no problem. But here we have taken degree, right? So 108 electrical degree per second square. Therefore alpha, the acceleration is this one, 108 electrical degree per second square. This unit, no, little bit to do it of your own, right? Now 12 cycles is equal to 12 by 60 because it is 60 Hertz system, so 0.2 second. Now change in delta. Delta will be half angular acceleration alpha into delta t square. So half, this is little bit you have studied in your physics, because joint entrance you have studied your lot of I mean mathematics, right? And so very hard preparation, right? So delta is equal to half alpha into delta t square, right? So half into this one into delta t is this much. So this is actually 2.16 electrical degree. And now alpha is equal to 108 electrical degree per second square, right? This is actually we make 18 RPM per second, right? So this is actually electrical degree per second square, right? So if what you do, 1 second you cube, another second you put in numerator. 1 second is equal to 1 upon 60 minute, right? So that's why 60 has gone up, and this is divided by 360. That's why it is 18 RPM per second, right? This way we have made this alpha has changed to 18 RPM per second, right? And rotor speed, we know that at the end of 12 cycle, we know synchronous speed is 120 F upon P. This we know. This will be your 4 pole, so it will be 1800 RPM plus alpha into delta T. So alpha is this much because it is in RPM we are considered into 0.2. So 1803.6 RPM. So machine will remain stable because synchronous speed is 1800 RPM, right? So this is little bit of change in, this is one way of making. If you want to make in other way also, no problem. If you find any alternative way, right? So this is how things are. Only you have to be alert about that changing to this thing. Like second square here means second into second, and 1 second is equal to 1 upon 60 minute. So 60 has gone to numerator into 180 divided by 360. So it is 18 RPM per second, right? So this way it has been made. Now another one, a 400 MVA synchronous machine, its inertia is H1 is 4.6 second, and a 1200 MPa machine H2, it is 3 seconds, right? The two machines operate in parallel in a power plant. Find out HEQ. This formula we have seen, the kinetic energy of the two machines, that is G1H1 plus G2H2. So this is 4.6 into 400 plus 3 into 1200. So this much of megajoule. And from equation 28, that whatever you have got, this 400 by your 100 into 4.6, there is 1200 into 3 by 100, right? So it is coming 54.4 megajoule per MVA, that is second. Therefore, equivalent inertia on a 100 MVA base, that is KE upon system base, that this much, this is 5400 divided by 100. So 54.4, same thing. This one and this one is the same thing, right? So this simple thing. Now this one, suppose a 100 MVA 2-pole 50 Hz generator has a moment of inertia as 40 into 10 to the power 3 kg meter square. What is the energy stored in the rotor at the rotor speed? What is the corresponding angular momentum? Determine the inertia constant H. Synchronous speed Ns is equal to 120 F by P, right? It is actually looks like zeta, no? It is Ns. Actually, that they are let's place this typographical thing. So this is a 3000 RPM, right? 50 Hz and 2-pole machine, and kinetic energy stored is half J omega M square. So half this J is given, and this is omega F to, you know, that is your what you call, that is 2 pi into 3000 upon 50 square, right? So this is actually this much of joule, right? And then kinetic energy H is K stored upon MVA. So same formula you will use, and M is equal to J into omega N. Same formula you will use, right? And M is equal to this much megajoule second per mechanical radian, right? So this way, your what you call that your these are the small simple problem. This is like a simple problem. So can you tell me one thing? If anybody, I hope you are listening all this. Achha, later I'll ask. A technical question, right? Anyway, later I'll ask. Now, power flow under steady state. Load flow studies, we have seen that power flow, that how power is flowing from one end to another end. For the purpose of basic understanding, we'll consider your short lossless transmission line. So transmission line has low loss, and we'll consider short transmission line, right? So this is actually a short transmission line. R is neglected. Sending end voltage is Vs, receiving end voltage is Vr, right? This is actually this thing, and your what you call, and we wish to determine the real and reactive power at the sending end and at the receiving end, given that Vs leads Vr by an angle delta. That means Vr lags Vs by angle delta, right? Therefore, on a per phase basis, power at the sending end, I mean, this is at the sending end, this is the current. Actually, current at the sending end and receiving end is same, II, right? Therefore, PS plus JQS is equal to VSI conjugate. And I is equal to Vs minus Vr upon Jx, right? So that means I conjugate will be Vs conjugate minus Vr conjugate, and it is conjugate. So instead of Jx, it will be minus Jx, right? Now, if you substitute here, Ss will be Vs into Vs conjugate minus Vr conjugate upon minus Jx, right? Now, Vr is equal to Vr angle 0. Therefore, Vr is equal to Vr conjugate is equal to magnitude Vr, and Vs is equal to Vs conjugate V, or what you call, sorry, magnitude Vs angle delta, because Vs is leading Vr by this thing, or Vr lacks this thing. If you take sending it as a reference, it will be minus delta then, right? So that is your magnitude Vs e to the power j delta. Now, if you substitute all this in terms of magnitude and angle, everything, then you will get, for a lossless short transmission line, Ps will be Vs Vr upon x sine delta, and Qs will be your what you call, just hold on, just hold on, just hold on, just hold on 1 minute, just hold on, just hold on 1 minute, just 1 minute. Sorry, that phone call came. Just hold on. All right. So anyway, so whenever you are this just hold on. Whenever you are making this, it will be Vs Vr upon x sine delta. Perhaps you might have studied electrical machine this kind of relationship, and Qs is equal to this much, right? Now, similarly, at the receiving end, if you try to find out, as it is a lossless line, that is R is neglected, short line, no charging admittance, so PR also will become Vs Vr upon x sine delta, and QR will become Vs Vr cos delta minus Vr square, right? This expression you can similarly, you can for receiving end also, putting the same logic, you can find out, right? Therefore, for a lossless transmission line, sending end power and receiving end power both are same, right? So Vs Vr upon x sine delta. Now, in similar manner, the equation for a steady state power delivered by a lossless synchronous machine is given by your PE is equal to PD, that is your EG into VT upon XD sine delta, right? Now, if you look, EG is the RMS internal voltage of the synchronous machine, VT is the terminal voltage RMS value, and XD is the direct axis reference, that is direct axis reactance of the synchronous generator, and delta is the electrical power angle. So same is P is equal to PD, that is EG VT magnitude of course upon XD sine delta, right? Now if you take a small example like your three-phase, your characteristic of transmission line you have studied, the sending and receiving voltage of a three-phase transmission line, right? Voltage of at 200 megawatt load equal to 230 kV. The per phase line impedance is J14 ohm, right? Calculate the maximum steady state power that can be transmitted. So your first you take that per phase, right? 230 into 3, it volts much of kV. Now when P, this will be maximum when delta will be 90 degree. So sine 90 is 1, right? So therefore your PR max is equal to PS max is equal to Vs Vr upon x, and both sending and receiving voltage are same, therefore Vr square upon x. So this much of megawatt per phase, because we have taken per phase voltage here, so multiply by 3, these are your this much of power, right? Now second one is, now look this one, a single line diagram of a system shown in figure this, all the values are power unit of a common base. The power delivered into bus 2, that is an infinite bus having a voltage of 1 per unit, right? And this is also 1 per unit, and 0.8 power factor lagging. Obtain the power angle equation and the swing equation of the system. Now, question is, what is infinite bus? Infinite bus means voltage and the frequency will remain constant, right? if I had taken the other course, at least theoretically, I should have told you how things are happened. So basically, voltage, magnitude, and frequency will remain constant. That means, suppose you have this system and you have another system, right? And this system capacity is very large. So if any disturbance happen to this side, right? Whatever dynamics will change to this side, it will not affect to the receiving, or what you call receiving side system, because its capacity is so high that whatever disturbance come to this side, there will be no effect on this side. That's why its voltage as well as frequency will remain constant. That is actually defined as unit your infinite bus. So this side, your what we call any changes, load and any dynamics changes, it will not be, this side cannot affect this, cannot disturb this side, because its capacity is so large, right, such that its voltage and frequency will be maintained constant. That's why for infinite bus, voltage, magnitude and frequency will remain constant. For our study, generally we assume one angle 0, right? This is the thing, unless and until something is specified. Now what you do, obtain the power angle equation and the swing equation. So you have to neglect losses. So this is parallel line, right? And this is basically what the another branch is created, this side half, right? So this is generator side reactance, this is transformer, and that's all, right? So now this side is generator, your what you call, you assume generator voltage is Eg angle delta, and these two reactants are in series, and this is your, this is connected, and this is another bus is created. This equivalent impedance diagram, and this bus voltage is 1 angle 0. This is infinite bus. Bus 2 is an infinite bus, right? Therefore, if you compute equivalent one, right, equivalent one, then what you will get? You will get 0.25 plus 0.15, right? Then this is your j 0.2, right? This is your 0.2 into 0.2 upon 0.4, because this bus 3 is created, but no fault, nothing is there. Basically, these two are in series. If you connect something here, then analysis will be different. But intentionally one bus bar is created, but this is actually j 0.2. This is also j 0.2, right? That's why it is your x equivalent. J is omitted here because every here also j, here also j, here also j, but later you consider. So this is your 0.5 per unit. And power factor is given cos phi 0.8, that is 36.86 degree lagging, 87 degree lagging. Therefore, current into bus 2, you find out that it is 1.0 divided by 1 into, because VI, your what you call this current into bus 2, that means whatever current is going into the bus 2, that is actually that means magnitude is 1.463 and delta is 20 degree, right? Just to compare. So this is your Eg and this is your delta. Now P is equal to electrical power is equal to Eg into Vt upon xq, because this voltage is Eg, we know that. This side is voltage is known and xq is known. So Eg into V2 upon xq, that is V2 sine delta. So whatever it is coming, that is P is equal to 2.926 sine delta. Now, if you know h by pi f d square delta upon dt square is equal to pi minus p, or this one pi minus p if it is in radian, if it is in degree, and pi is equal to 1 per unit mechanical power input to the generator is given. Therefore, the swing equation d square delta upon dt square is equal to this much, right? As a verification of the result at steady state, pi is equal to p is equal to 1, right? If you do so, 2.926 sine delta is equal to 1, therefore delta is equal to 2 degree, 20 degree. So look, this delta is equal to 20 degree, right? So today up to this one, right? And due to something I'll be busy, but I'm not stop presenting. Now my question is that next week I will take class at a stage, right? And after that, that symmetrical component, because symmetrical fault, only one numerical I have explained that day. I will take only numericals, and last chapter whatever I have mailed AGC, it should not be there in your course. That is true, right? And stability, still something will be there. Before leaving, one small question I'll ask. You can answer. My answer, I am not satisfied. Those who are in physics, this is a physics answer. When sun is rising or sun is setting, it looks very large. When it is on the top of the sky, it looks like very small to our eyes. What is the reason? Physics, because you have studied physics. What is the reason? Anybody can tell? Such that I can rectify my answer. Any idea? When sun is rising, it looks like a very big size, right? And when setting also, it looks like that. But when it is going on top, it looks like to our eyes that as if that diameter has reduced, right? What is the reason? Anybody can tell? Tell something you tell before leaving.
So possibly refraction or something.
No, a little bit of something. Whatever you are telling, little bit different way. I do not know. I do not know. I had one friend. He nearly of my age. I asked him, and I mean when we were studying together in the hostel, right? And at that time, he is now CEO of one Indian company. I'll not tell the name, right? And but anyway, so he told me something. Any other thing, whatever you are telling, that is, I will accept that, but a little bit better way, whatever he said, right? I do not know. I asked him actually. Anybody else? Ovinandan has said something. I cannot deny that. Whatever you said, it is yes, to some extent, of course. Anything else? Anyway, thank you. So due to some reason, this thing yesterday, your Spring Fest was there, but anyway, I didn't go. But number of due to COVID protocol, everything was maintained. But anyway, I was also surprised when I see in campus that Spring Fest thing is there, and singers came and anyway. Hopefully that there is no further version of this COVID. 2 years, it has spoiled the life of whole world actually, right? Anyway, thank you very much. And next week, I think many of you may be in the campus or by returning in the campus. I'll take class till 28th March, right? This week, this thing, only this chapter. This will not be there. Some more is there. Transient stability part is there. But next week at a stretch I'll take, and after that all numericals for all the 3 chapters, such that you can do well in the exam. And regarding assignment, whatever I have given, keep ready. Your last date of submission will be 4th April, on or before. I'll tell you. At least I'll tell you next week when you will submit, and such that this thing, and I told you everything about that, right? So 30 marks will be next 2 hours exam. It cannot be more than 2 hours exam, and 30 marks, right? And on 3 chapters only, try wholeheartedly, those who are coming and listening to the class, right? So thank you very much. Then I'm leaving next week. Next Monday I'll take class. Not much left in the syllabus, right? And thank you very much. Thank you very much. Okay, so I'm leaving now. So next class will be next week then, right? Okay.